Today we're going to take a look at vectors in this video. You will learn how to add them, subtract them, find out what you get when you add a couple of different vectors. You've already been introduced to some of those vectors. Previously we've taken a look at vectors of velocity, displacement, and acceleration. A vector is a quantity that requires both a magnitude, a size, and also a direction. So here you see the three vectors listed, and the arrow on top of each of these indicates that it's a vector quantity. Without that arrow on it, it would not be a vector quantity. Vectors are different from scalars because of their dependence upon having a direction. Here you see several scalars. You see V without the arrow on top is speed. So you can indicate the speed of your car without any regard as to what direction you're going. It would not make sense to talk about a direction associated with a temperature and money. Money is another quantity, popular one, and that to add a direction to your money would also be kind of a silly concept. We're going to draw vectors, and there are going to be two parts to that drawing. Here you see a straight black line going from left to right, and the length of it is to scale. So that would be 60 meters per second going east. And if I were to draw another line that was half that length, I'll approximate that, then I would have a line or vector the length of whose line indicates it is going 30 meters per second if it's to the same scale. So the scaling exercises we did for graphs are going to come in handy. If this was 1/3 of the original black one there, it would probably look and measure out to be 20 meters per second. As long as the vector is the same length to indicate the size of the quantity being measured and goes in the same direction, it is the same vector. So take a look at these three vectors. You've got three vectors here, A, B, and C. Now, they're all the same length, so they have the same magnitude or size, and they're all going in the same direction. So you could say that vector A equals vector B equals vector C. Now take a look at the two vectors here, X and Y. That X is that long, and it's got its arrowhead, and Y is that long, has its arrowhead. That vector X would be equal to Y because they're both the same magnitude or length, and they're going in the same direction. But they are not, vector Z right here, they are not equal to vector C, because vector Z is going in the other direction, so it would not be equivalent to X and Y. Now, if we're going to add vectors, what we do is we follow the tip to tail rule. So here you see a vector A. I'm just going to retrace it right here on the board, and that would be vector A. Now vector B might have been up here. I'm trying to draw that to the same size and direction, and that we moved vector B down to there. Okay, that's just a line for the fact that it's moving. That is not a new vector I'm drawing on there. So B is moved down, and the tail of B, if you think of it as an arrow, is right here at the tip of A, and it still has the same direction and magnitude. So that would be how you would add vectors together, and then we'll take a look at what you get as a result. So now that we've added vector A to vector B, that we can find out what the net displacement, or how far you've gone from the very beginning of your journey here at A up to where you ended with vector B right here. And so this is now vector C, and it is called a resultant, which pretty obviously comes from the word result, because that's what the result is when you add A and B together. Notice that it has its own direction, and you can look at it as though it is a shortcut, because if A and B were how you walked straight here along A, then you went straight along B, that it would be just the same as if you had taken a shortcut from the beginning of A to the end of B. Now let's look and see what happens when Sue drives 2 miles east to pick up Sam. So this would be her initial trip to pick up Sam, and then she's going to go another mile in the same direction to get to school. And so the second section of her trip, the tail of it right there, is added to the tip of the first arrow. Now they are added together, and let's take a look and see the So here on this slide we've now got the resultant, which is 3 miles east. It starts at the same place as the original first vector, and then it ends where the second vector ended, and that we see that Sue's vector, or displacement, goes 3 miles to the east. The two vectors were in the same direction, so you just get one vector that's longer. Now here's Irene driving around town. She drives 3 miles straight to the east, so she is moving from here to here, and when she gets 3 miles east, she's at McDonald's. She grabs lunch, and then she drives back the exact opposite direction. She goes 1 mile west to get to school. And so those two vectors, that the tail of this one is at the tip of the first one right here, and we've added them together. The result would be, the result here would be a vector that starts where Irene started in the first place, and then ends where she ended up after doing the two different sections of her trip. And so we can see that the resultant here is 2 miles to the east. Let's do another variation of adding vectors, except this time the vectors are not going to be going in the same direction, nor are they going to be going in exact opposite directions as in the previous examples. And so here Jenny drives 2 miles to the east, and we see a vector that's to scale down on the bottom of the drawing. And now we're going to do a second leg of the journey, where she then drives 1 mile north to pick up John. Okay, Jenny has now made it to John's house. She had started out here. I didn't have the right tool turned on Smartboard here, and she had ended up here on the first leg of her journey. The second leg of her journey, we put the vector that goes 1 mile north at the tip of the first vector, and then it goes straight north and goes up there. So now we've added those two vectors together as tip to tail. Now here is the resultant that we have in red, that goes from where her journey started to where it ended. And it would be as though she had started out at this angle that's shown there as 26 degrees and gone straight to her final destination. That the resulting vector does not change at all regardless of how she got there. It's just a matter of she now had a net displacement of, here it shows 2.2 miles to the northeast. The length of this is not as easy to come by as with the vectors that were going in the same direction or exact opposite directions. So you have two choices. You could measure the length of this vector with the same scale that you drew the first two vectors, and you should get something at 2.2 miles to the northeast. The indication here of the angle that results between the resultant and the initial vector, you could measure that with a protractor. Now, as somebody has probably already noticed, I've got a right triangle here. So I've got a 90-degree turn right here in the corner. And so we can find out the length of the resulting vector by just using the Pythagorean theorem. So if this side of the triangle is A, and this is B, and this is C, then you can use your old friend Pythagoras' theorem, A squared plus B squared is equal to C squared. You will have to use that equation to solve some of the problems in this unit. I hope that introduces you to the basics of this. I'll see you in class, and we'll be adding some vectors. Thank you very much.